Hello and welcome to the AI Research Roundup. I'm your host, Alex. Today, we're diving into a fascinating paper focused on applying AI to medical diagnostics, specifically electrocardiograms, or ECGs. The paper is titled GEM Empowering MLLM for Grounded ECG Understanding with Time Series and Images, published just recently on March 8, 2025. So, the researchers introduced GEM, which is the first multimodal large language model designed to really understand ECGs by combining time series data, the actual signal, with the visual ECG images and text. Essentially, it aims to improve how AI interprets ECGs by better linking diagnoses directly to specific waveform evidence, making it more explainable and aligned with how clinicians work. Alright. And building on that goal of better ECG understanding, the researchers have actually made their work quite accessible. What we're seeing here is essentially the project's home on GitHub. So, if you're interested in digging into the technical side, this is where you'd find the actual code for GEM, along with setup instructions, scripts for training and evaluation, and guides on preparing the specific ECG datasets needed to replicate their work. It's really helpful for reproducibility. Okay, so this figure here, figure 1, really illustrates what GEM can do in practice. You see a standard 12-lead ECG image on the left. Then, on the right, GEM provides a detailed interpretation. It identifies several key findings, like a previous infarct, premature contractions, and a bundle branch block. Importantly, it highlights specific evidence for each finding directly on the ECG waveform. See those numbered boxes? This really shows that feature-grounded analysis and evidence-driven reasoning the paper emphasizes, making the diagnosis much more transparent. Okay, so building on that example we saw in Figure 1, this next figure, Figure 2, gives us a look under the hood at GEM's actual architecture, how it works. You can see it takes in both the raw ECG signal, the time series data, and the transformed ECG image. It uses separate encoders, specialized components, to process each of these. Then, crucially, it uses what they call cross-modal alignment learning to bring the information from both the signal and the image together into a space the language model can understand, before generating those detailed language responses we saw earlier. It also shows this interesting part about generating training data using other models like GPT-4o. Alright, so we just saw the architecture in Figure 2, including how GEM generates its own training data. Now, Figure 3 here really highlights the difference it makes. On the left, you see the older ECG instruct data format, which was less detailed and didn't always link findings clearly to the waveform. But on the right, this is the new ECG grounding data GEM creates. Notice how much richer the answer is. It specifically points out features like irregular RR intervals or negative QRS complexes in certain leads, providing that explicit evidence we talked about. This better data is really what enables GEM's improved grounding. Okay, so that richer ECG grounding data we just saw really pays off, as shown here in Table 2. This table gives us some hard numbers comparing GEM, specifically 2 trained versions against the previous pulse model. It's looking at how well they perform on the MIMIC IV ECG dataset, using metrics like ECG feature grounding, evidence-based reasoning, and clinical diagnostic fidelity. And wow, the difference is clear. GEM scores around 75 points in these areas, whereas Pulse is way down around 50 to 52. This really quantifies how much better GEM is at linking findings to evidence and reasoning in a clinically relevant way. Right. And Table 1 here gives us Part 1 of those grounded ECG understanding results we were just touching on with Table 2. Again, it's comparing GEM against Pulse on the MIMIC IV ECG data. So, looking at these specific metrics, we see diagnosis accuracy jumps from about 76% for Pulse to over 86% for both GEM versions. And look at the analysis completeness and relevance, huge improvements there too. Perhaps most striking are the lead assessment scores. Coverage jumps from under 6 to over 51, and accuracy from 2 to over 3.3. It really shows GEM is much better at detailed lead level analysis. Okay, so we've seen how GEEEM improves on those detailed grounding metrics. Now, Table 4 here shifts focus slightly to look at performance on the ECG benchmark, specifically on tasks like generating reports and answering questions, ECG QA. So, for the PTBXL report score, GEM, particularly the SFT Pulse 7B version, scores 67.1, which is a nice jump, about a 5.8% improvement over the previous Pulse model's 61.3. And then for ECG QA accuracy, well, GEM maintains a very similar strong performance to Pulse, around 73%. So it's improving report quality without losing ground on question answering. Alright, so after looking at report generation and QA in Table 4, Table 3 here gives us another slice of the ECG bench results, this time focusing purely on ECG abnormality detection. It compares GM against Pulse and other baselines across several different datasets, like PTB-XL Super, Code 15%, and others, using standard metrics like AUC and F1 score, overall GEEM. Particularly the SFT Pulse 7B version consistently matches or slightly improves upon the Pulse model's strong performance across these varied datasets, showing its robustness in detecting abnormalities. Okay, so wrapping things up on GM today, we've seen across these results how it significantly improves the grounding of language models to the actual ECG data, using both the time series signals and the lead images effectively. This leads to better reports and more detailed understanding. Ultimately, this kind of work is vital, pushing AI towards genuinely understanding complex medical information, a key step for future clinical tools. Well, that's our time for this AI Research Roundup. Thanks for listening. I'm your host, Alex.